Somewhere inside Microsoft's headquarters, an engineer just flipped a switch that quietly rewrote the security of every Windows machine on the planet. Not because of a new virus, not because of some hacking scandal, but because of a threat that doesn't even fully exist yet. A quantum computer powerful enough to crack the encryption protecting your emails, your bank records, and your passwords. Microsoft isn't waiting around to find out when that machine gets built. The company is racing to build it themselves, and at the exact same time, quietly re-engineering Windows itself to survive the moment it arrives. For most people, quantum computing still sounds like a distant science experiment, something happening in a university basement with no real connection to the laptop sitting in front of you. That assumption just became noticeably harder to defend. Over the past year, Microsoft has been moving on two fronts simultaneously, and almost nobody outside the tech press has connected them into a single story. On one front, the company is building its own quantum computer chip, betting nearly 2 decades of research on an approach almost nobody else in the industry is willing to touch. On the other front, Microsoft has already started quietly rebuilding the cryptographic foundation of Windows itself, specifically to survive an era when quantum computers become powerful enough to break the encryption the entire internet currently relies on. Let's start with the hardware, because it's the more dramatic half of this story, and it comes with a genuinely scientific gamble attached. In February of 2025, Microsoft unveiled a chip called Majorana 1, which the company described as the world's first quantum processor built around something called a topological qubit. Most competing quantum computers, including the ones built by Google and IBM, rely on superconducting circuits or trapped ions to store quantum information. Microsoft chose a completely different path nearly 20 years ago, one based on exotic particles called Majorana zero modes, which aren't really particles in the conventional sense, but strange quasi-particle states that emerge under very specific physical conditions. Here's why Microsoft bet on something so unusual instead of following the crowd. Most qubits are extremely fragile, prone to losing their delicate quantum state from the tiniest disturbance, a problem called decoherence that has plagued the entire field for decades. Topological qubits, in theory, offer something fundamentally different. Because the quantum information gets encoded across the overall shape or topology of the system, rather than stored in one fragile location, small local disturbances shouldn't be able to destroy it nearly as easily. If that theory holds up in practice, topological qubits could require dramatically less error correction overhead than every other quantum computing approach currently being pursued, which would be an enormous engineering advantage if Microsoft can actually deliver it at scale. That giant if is exactly where things get genuinely contentious, and any honest breakdown of this story has to sit with that tension rather than smooth it over. Microsoft's topological qubit claims have faced serious, sustained skepticism from parts of the physics community since well before Majorana 1 was even announced. The core problem is that proving a Majorana zero mode actually exists, rather than something that just looks similar in certain measurements, is notoriously difficult. And Microsoft has faced public scrutiny over exactly this question more than once. In fact, a peer-reviewed critique published in Nature specifically challenged aspects of Microsoft's methodology, alleging coding errors and selectively presented data in earlier work. Microsoft has firmly stood behind its physics and disputed the characterization, but the timing of that critique's publication, arriving just as Microsoft was promoting its newer chip, made the disagreement considerably harder to quietly wave away. Speaking of that newer chip, Microsoft unveiled Majorana 2 at its Build Developer Conference in June of 2026, and the company used it to make a genuinely bold claim. According to Microsoft, the new processor achieved topological qubit lifetimes exceeding 20 seconds, more than 1,000 times longer than what earlier devices could manage. The company says it achieved this improvement partly by swapping aluminum for lead in its superconducting material stack, and partly by redesigning the underlying semiconductor structure to more than double what physicists call the topological gap, essentially a kind of energy buffer that helps protect the fragile quantum state from environmental noise. Microsoft also mentioned using artificial intelligence techniques to help refine the chip's design, which is its own small, interesting subplot buried inside a much bigger story. If that 1,000-fold stability improvement genuinely holds up under independent scrutiny, it would represent a meaningful validation of an approach the broader scientific community has treated with considerable suspicion for years. That's a big if, worth repeating clearly rather than glossing over. Skeptics within the quantum computing community will almost certainly want to see this replicated and independently verified before treating it as settled, established science, rather than an impressive but still contested internal claim. Science reporting in this specific area has a well-earned reputation for excitement running ahead of confirmation, and Microsoft's topological qubit program has already been at the center of exactly that pattern more than once. Regardless of how that specific scientific dispute eventually resolves, Microsoft has attached real, specific numbers to its ambitions. Those numbers deserve scrutiny. Advanced quantum processors from any company using any architecture are still measured in the hundreds of qubits, not the millions. That gap between today's hardware and Microsoft's stated 2029 target is genuinely enormous, and it's worth sitting with that scale honestly rather than assuming the timeline is simply guaranteed to arrive on schedule. Now here's where this story stops being purely about exotic physics in a research lab and starts becoming something that actually touches your computer directly. Whether or not Microsoft's specific chip architecture ultimately succeeds, quantum computers, if they eventually reach sufficient scale and reliability, pose a genuine, well-understood threat to the cryptographic systems protecting essentially the entire internet today. Most of the encryption securing your emails, your banking transactions, your saved passwords, and your private messages relies on mathematical problems that are extremely difficult for classical computers to solve. Things like factoring extremely large numbers. A sufficiently powerful quantum computer running a specific algorithm called Shor's algorithm could theoretically solve those same mathematical problems dramatically faster, potentially unraveling encryption that would otherwise take classical computers thousands of years to break. This isn't some far-off, purely theoretical concern that security experts are worrying about for fun. There's a specific named threat model built entirely around this risk called Harvest Now, Decrypt Later. The idea is straightforward and genuinely unsettling once you sit with it. Adversaries, including hostile foreign governments, don't need a working quantum computer today to benefit from this attack. They simply need to intercept and store encrypted data right now, while it's completely unreadable, and wait patiently for quantum computers to mature enough to crack it open later. Government communications, financial records, and long-term confidential business data are all sitting in encrypted storage right now, potentially already being harvested by someone patient enough to wait for the decryption key to eventually arrive. This is exactly the threat Microsoft has been quietly preparing Windows itself to withstand, and the timeline on this side of the story is considerably more concrete and less speculative than the exotic chip physics we just covered. Microsoft's core cryptographic library, called SymCrypt, which underpins security across Windows, Azure, and Microsoft 365, began receiving what are called post-quantum cryptography algorithms back in December of 2024. These new algorithms, with names like MLKEM and MLDSA, are specifically designed to remain secure even against an attacker armed with a fully functional quantum computer, because they're built on entirely different mathematical foundations than the encryption methods currently in widespread use. By November of 2025, these post-quantum algorithms had reached general availability directly inside Windows 11 and Windows Server 2025, meaning they aren't experimental features buried in a developer preview anymore. They're shipping functioning cryptographic tools available right now on production systems running in homes, offices, and data centers around the world. As of May 2026, Microsoft extended this even further, bringing support for issuing post-quantum digital certificates directly into Active Directory certificate services, the backbone infrastructure that countless enterprise networks depend on for identity verification and secure communication. What makes this rollout particularly interesting from an engineering perspective is something Microsoft calls composite cryptography. Rather than simply ripping out old encryption methods and replacing them entirely with new post-quantum algorithms overnight, Windows is being updated to run classical and post-quantum algorithms together simultaneously, as a kind of belt and suspenders approach. In practice, this means an attacker would need to break both the traditional encryption method and the new quantum-resistant method at the same time to actually compromise protected data. Microsoft calls this defense in depth, and it reflects a broader philosophy the company refers to as crypto agility, building systems flexible enough to swap in newer, stronger algorithms as cryptographic standards continue to evolve over the coming years, rather than assuming today's post-quantum algorithms are automatically going to be the final permanent answer forever. If you're finding this breakdown useful, go ahead and hit that subscribe button, because we cover stories exactly like this every single week, connecting the dots between breakthroughs that most channels cover in isolation. Microsoft has actually published a fairly detailed, specific timeline for this entire transition, and it's worth walking through because it reveals just how seriously the company is treating this threat internally. The company's stated goal is to complete a full transition to quantum-ready cryptographic standards across its systems by 2033, with early adoption of core protections beginning back in 2029. That 2033 target actually sits 2 years ahead of deadlines set by most government bodies working on the same issue, and Microsoft has specifically said it expects to meet the more aggressive requirements laid out in something called CNSSP 15, a policy governing national security systems that mandates adoption of next-generation cryptographic standards starting in January of 2027. When a company voluntarily sets internal deadlines tighter than what most governments are currently requiring, that tends to signal genuine institutional urgency rather than simple regulatory box checking. This broader effort touches far more of the Microsoft ecosystem than just the operating system itself. The company has stated its intention to extend post-quantum protection across Azure cloud services, Microsoft 365 productivity tools, its various data platforms, its networking infrastructure, and even its artificial intelligence services. Beyond its own products, Microsoft joined the Open Quantum Safe project as a founding member and led a specific integration effort within the National Institute of Standards and Technology's own post-quantum research initiative. The company's Frodo-Chem cryptographic system, developed in collaboration with outside academic researchers, is currently positioned to become an internationally recognized cryptography standard through the International Organization for Standardization. This isn't a company quietly reacting to a distant hypothetical threat. This is a company actively trying to help write the rulebook the entire industry will eventually have to follow. So let's step back and connect these two halves of the story, because that connection is really the entire point here, and it rarely gets made explicitly in most coverage of either topic individually. Microsoft is simultaneously racing to build one of the quantum computers that could eventually threaten today's encryption standards, while also racing to protect its own massive software ecosystem against exactly that same threat, regardless of which company ultimately wins the broader quantum computing race. That's not actually a contradiction, even though it might initially sound like one. It reflects a company hedging its bets across an entire technological transition, rather than betting everything on a single outcome. If Microsoft's own Majorana architecture succeeds and becomes commercially dominant, the company is positioned at the center of the next major computing paradigm. If a competitor gets there first instead, using superconducting qubits, trapped ions, or some other architecture entirely, Microsoft's Windows and Azure ecosystem is already being prepared to survive that outcome, regardless of who built the winning machine. There's also a genuinely fascinating business logic sitting underneath all of this technical detail, one that connects directly back to why this story genuinely matters for Windows specifically, rather than existing as some separate, unrelated announcement happening in a different corner of the company. Microsoft's entire commercial identity is built around trust in its software security, particularly among enterprise customers, government agencies, and regulated industries that can't afford even a hint of vulnerability in their infrastructure. A company whose products get compromised by quantum computing before its competitors have prepared equivalent defenses would face catastrophic reputational and financial damage, especially given how deeply embedded Windows and Azure already are inside government and financial systems worldwide. Getting ahead of this transition publicly, with specific dates and concrete technical milestones, isn't just responsible engineering. It's also a serious competitive positioning move against Amazon, Google, and every other major cloud and operating system provider racing through this exact same transition right now, mostly with far less public detail about their own specific timelines. It's worth pausing on exactly why enterprise IT teams should care about this transition well before any quantum threat actually materializes, because the migration itself is genuinely complicated in ways that go far beyond simply installing a routine software patch. Microsoft's own guidance recommends organizations begin by inventorying every place they currently rely on public key cryptography, then specifically prioritizing systems that protect long-lived, highly sensitive data, things like document repositories, email archives, and backup storage that could remain valuable to an attacker for years or even decades after being stolen. That inventory process alone can take enterprise security teams months to complete properly across a sprawling modern technology stack. Layer on the additional work of testing hybrid and composite cryptographic approaches inside non-production environments before ever touching anything live, and you start to understand why Microsoft keeps repeatedly describing this transition as a multi-year undertaking, rather than something resembling a single flip of a switch. Waiting until quantum computers actually arrive at threatening scale before starting this work would leave organizations scrambling under genuine time pressure, precisely the scenario Microsoft's security leadership has publicly warned against more than once. There's also an interesting wrinkle specific to hardware security modules, the specialized physical devices many large organizations use to store their most sensitive cryptographic keys under extremely tight physical and digital protection. As of early 2026, post-quantum support for these hardware-backed keys remains incomplete across parts of Microsoft's Azure Key Vault service, with full general availability still rolling out gradually through 2026 and into 2027, depending on the specific tier and region involved. Token signing services and much of the internal service-to-service communication happening constantly behind the scenes across Azure still rely primarily on classical pre-quantum cryptography for now. This detail matters because it's a useful, honest reminder that even a company moving as aggressively and publicly as Microsoft still has meaningfully far to go before its own infrastructure is fully quantum ready from top to bottom. The foundational pieces are genuinely in place. The complete end-to-end rollout across every corner of a company this large is still very much a work in progress, exactly as Microsoft itself has repeatedly acknowledged in its own public roadmap documents. Government deadlines add yet another layer of pressure shaping this entire timeline, and they vary considerably depending on which country and which specific industry you happen to be looking at. The United Kingdom's National Cybersecurity Center has told the country's key sectors and critical organizations to plan for a full switchover to post-quantum cryptography by 2035, a full 2 years later than Microsoft's own internal 2033 target. The United States, through its Committee on National Security Systems Policy, has set a considerably more aggressive requirement, mandating adoption of next-generation cryptographic standards for new national security systems and products starting in January of 2027, less than a year from when this video is being made. Microsoft has explicitly stated it expects to meet even that more demanding American deadline, while simultaneously monitoring similar, still evolving initiatives taking shape in Australia, Canada, the European Union, and Japan. Watching a single company try to satisfy multiple staggered international deadlines simultaneously gives you a genuine sense of just how fragmented, and still actively being negotiated, the global response to the shared quantum threat currently remains. There's one more angle worth including before we wrap up, because it circles back nicely to that opening claim about Windows itself. Developers building on Microsoft's platforms aren't being left out of this transition either. Starting with .NET 10, Microsoft made post-quantum cryptography support generally available directly inside its widely used development framework, meaning software engineers building applications for both Windows and Linux can now integrate quantum-resistant encryption using the same familiar tools they already rely on daily, without needing to bolt on entirely separate, unfamiliar cryptographic libraries. That kind of native, low-friction integration tends to matter enormously for how quickly new security standards actually get adopted in the real world. A security feature that requires specialized expertise or a completely separate tool chain to implement often sits unused for years, while one baked directly into the tools developers are already using every single day tends to spread far more quickly across the wider software ecosystem, often before most end users ever notice or fully understand exactly why it happened. None of this means quantum computers are about to start breaking your passwords next week, and it's worth being genuinely clear about that before wrapping up. Currently, quantum hardware, including Microsoft's own most advanced Majorana 2 chip, remains dramatically far short of the scale needed to actually threaten real-world encryption in practice. Breaking modern public key cryptography using Shor's algorithm would require millions of stable, error-corrected qubits working together, and today's most advanced quantum processors from any company are still measured in mere hundreds. The genuine urgency here isn't about an imminent attack happening tomorrow. It's about the multi-year lead time required to migrate enormous, deeply embedded software ecosystems like Windows and Azure before that threat eventually does mature, whenever that timeline actually arrives. What makes this moment worth paying attention to, even with all of that healthy skepticism intact, is the sheer scale of institutional commitment now visible from a company as consequential as Microsoft. This isn't a speculative blog post from an enthusiastic startup trying to attract venture funding. This is the company behind Windows, Azure, and Microsoft 365, publicly committing specific technical resources, concrete calendar deadlines, and its own internally built quantum hardware program to a transition it clearly believes is coming, whether that arrival happens in 2029, 2033, or sometime meaningfully later than either of those dates. When an organization operating at that scale moves this deliberately and this publicly, It's a meaningful signal about where serious institutional money and engineering talent currently believe the future of computing security is actually headed. If you want to keep following where this goes next, make sure you like this video and subscribe so you don't miss the follow-up. Because both halves of this story, the chip and the cryptography, are moving fast enough that the next update is probably closer than you think.